Hello, this is video number 3 of sections 2.9 and 2.10 or 2.10, which has to do with the quotient rule and the complete set of trigonometric derivative formula shortcuts. Yeah, that's what we're doing. In this video, what I wanted to do is do a couple of these examples with you in terms of applying the quotient rule. Remember that the quotient rule, the word quotient is really the name that we give to the answer that we get whenever we're dividing. So some people call this the division rule, but most people call it the quotient rule. So if I ever have a division going on, whenever I have a numerator and a denominator, and I have functions on top and on bottom, then I'm probably going to use the quotient rule. I want to warn you that even though I'm looking at examples 1, 2, and 3 as being quotient rule eligible, it turns out one of them we can do a little bit faster and not have to set up the quotient rule. So let's start with example 1. And we're going to do 1 and 2 in this video. We'll do example 3 in the next video. So example 1 says, hey, let's find the derivative. And I know they're asking for the derivative because they're using this notation. This is the Leibniz notation, dy over dx. It says we're finding the derivative of the y equation with respect to x. Well, here's my y equation, and it is in terms of x. But I notice that we have a numerator and we have a denominator. We have what some people would call the dividend and the divisor, right? We're dividing two things, blue divided by red. So we're going to do the quotient rule. The quotient rule says to find the derivative, we need to take the derivative of the numerator, the derivative of the top, times the bottom, the denominator, minus the derivative of the denominator times the top, multiplied by the top, or the numerator, and then all of that divided by the square of the denominator, the square of the bottom. So x squared plus 1, everything squared. This is the setup that's going to give us the correct derivative formula for this equation y. Again, once we find the derivative formula, we have now found the formula that will find the slope of the tangent line at any x value. It'll find the instantaneous rate of change at any x value. It'll find the derivative at any x value, because all those three things mean the same thing. I hope you're starting to hear it in your head that whenever I say derivative, it's the same thing as instantaneous rate of change, which is the same thing as the slope of the tangent line. All right, so let's start taking derivatives. So when I take derivative of this blue part, the derivative of 5x minus 2, well, I can take the derivative of 5x, which is 5, minus the derivative of 2. 2 is a constant. Constants never change, so therefore their derivative is 0. And so my derivative of the blue part is just 5, times x squared plus 1, minus the derivative of x squared plus 1. Well, the derivative of x squared would be 2x, plus the derivative of 1 would be 0, so that's gone, times 5x minus 2. Notice that as I'm doing this, I'm keeping things in parentheses just in case I need to be very, very careful, and I should be very, very careful with my factors. Okay. Have I taken all the primes? Because if I have, if you are working on a free response question, if you leave it like this is the derivative, right? It's not simplified, but it is a derivative. Now, if you're working in a multiple choice part, this is probably not one of the answer choices that they give you, because they're going to give you the most simplified version. What would that be? I don't know. Let's see. It could be this. If we distribute the 5, we'll get 5x squared plus 5. If we distribute the 2x, I'm going to get 10x squared minus 4x. Except we were subtracting. So that means I have to subtract, and I have to subtract, which is going to make this into a plus 4x. And all of that is still divided by x squared plus 1. I would not encourage you to multiply this out. I would leave it like that. And then I guess we could give the final answer as, let's see, 5x squared minus 10x squared. I believe that's negative 5x squared. And then plus 5 and plus 4x I cannot put together, so I'm just going to say plus 4x plus 5 all over x squared plus 1 quantity squared. So what this means is I found the derivative formula. I found a derivative function. The purpose of the derivative function is, if I told you for this equation, y equals 5x minus 2 divided by x squared plus 1, can you find the slope of the tangent line at x equals 2? All you have to do is substitute a 2 in wherever you see an x in this formula, and it's going to spit out that slope. Or if I ask you find the instantaneous rate of change at time 0, well, all you have to do is substitute a 0 wherever you see an x, and whatever that comes out to, that would be the instantaneous rate of change at x equals 0, because this finds the derivative value at any x point. We don't have to do that, however, for example 1. Example 1 was just finding the formula. This is the formula, and we're done. Remember, this was an answer, not simplified. This is an answer a little bit more simplified. I would not try to factor out the quadratic unless you think it might cancel one of the x squared plus 1s, but I don't think it will, so I think we're good. When I look at example 2, I notice that there's also division, but this division includes a constant in the denominator. And whenever there's a constant in the denominator, I could do the quotient rule, remembering that when I take the derivative of the bottom, it'll be 0. So whenever in the setup, wherever I do the derivative of the denominator, the derivative of 7 would be 0. However, whenever we're dividing by a constant, it's going to be a lot of time saved if we rewrite it. Notice I'm not finding the derivative. I'm just rewriting the original function, because dividing by 7 is the same thing as multiplying by 1/7. And so if I rewrite it like this, I don't have to use the quotient rule. I don't even have to do the product rule, because one of the things I'm multiplying is a constant. So I can use the constant multiple rule, which says if you're taking the derivative of a constant times a function, hold the constant, find the derivative of the function, and then multiply it back in. Well, let's find the derivative of the function that's inside the parentheses. So 3x squared, the derivative of this would be 6x, minus the derivative of 2x would be 2, plus the derivative of 3 would be 0. So therefore, this is my derivative function. That's a lot quicker than setting up the derivative of the top times the bottom minus the derivative of the bottom times the top all over the bottom squared. I do want to say that if you do apply the quotient rule to this, you are going to get the correct answer. It's just going to be a little bit lengthier, right? So some students, whenever they see a division like this setup, they're always going to do the quotient rule, because they're like, that's what their brain tells them to do. But if you see that there's a way to save time, like scooting out that constant in the denominator as a 1/7 multiple, then it might save you some time. That wasn't the end, though. They wanted us to find the derivative at 2. So f prime at 2 would be 1/7 times 6 times 2 minus 2. I'm going to put this in parentheses there, which means this would be 6 times 2 is 12. 12 minus 2 is 10. So then this is really 10/7. That is my derivative value at x equals 2 for this function. That is the slope of the tangent line at x equals 2 of this function graph. And that is the instantaneous rate of change of this function at x equals 2. We're going to pause this video. We'll come back and do example 3, and then we'll look at some of those graphs that we see at the bottom of the page.